The camera opens on a strange sky, not black and starry, but mottled with tiny speckles of red and blue. It is a full sphere unwrapped into an oval map, like the peel of an orange pressed flat. This is not an artist's painting. It is a photograph of the oldest light we can see, the faint afterglow left when the universe was less than a heartbeat old. Every little patch glows with a slightly different temperature, a fossil imprint of sound waves that once rippled through newborn space. From this delicate pattern, scientists pull out a number. They feed the map into their equations, compare the size of the ripples, trace how matter and light dance together in that first, dense fog. Out comes a prediction for how fast space should be stretching today. One value, a single rate, written in units of distance and time, as if the universe had signed its name on the sky billions of years in advance. Then the scene cuts to a different sky. Now we see a swarm of galaxies scattered across the darkness, each one a pale blur, some tinged red, some blue, all tagged with thin lines of data. These are not ancient ripples frozen in place. These are islands of stars in motion. Their light has been stretched as space grew while it traveled, shifting spectral lines toward the red. Measure how much the light has shifted. Measure how far away the galaxy is. You get another way to compute how fast space is expanding now. Two skies, two methods, two answers for the same cosmic question. The number wrung from the ancient afterglow is lower. The number read from the nearby galaxies is higher. On a chalkboard, the difference looks modest, a few units, easy to dismiss as a nuisance. Let those numbers run for billions of years. Though, and they trace two different histories, two versions of how quickly reality has been pulling itself apart. How can one universe carry two incompatible biographies? Imagine walking into a quiet room where two clocks hang on the same wall. Both are beautifully made. Both were checked that morning. Their gears turn smoothly. Their faces are clean, but one insists it is early, while the other claims the day is already half gone. You listen for a rattle. You search for a cracked gear. You find nothing obvious. Which do you believe? Do you reset one? Or admit that something about the room itself might be playing a trick? On the largest possible scale, we are standing in that room. One clock is built from early light, from that ancient afterglow stretched across the sky. The other is built from a ladder of distances here and now, from stars whose brightness can be calibrated and explosions whose power can be standardized. Each clock has been checked, cross-checked, and refined. Each has passed internal tests, yet they disagree about the pace of the same expansion that carries us all. At first, cosmologists blamed the usual suspects. Dust in the wrong place could dim a galaxy and trick us about its distance. Subtle biases in how stars are selected could bend the ladder. Perhaps a small oversight in how the early universe was modeled could skew the reading from the afterglow. That is what you expect when two careful measurements do not line up. Improve the data, improve the methods, and the numbers should drift together. They did not. As observations sharpened, the gap hardened instead of fading. The early light remained loyal to its slower value. The local measurements continued to push for a faster pace. More teams joined the effort, using new telescopes, different stars, exotic beacons such as masers and distant explosions. The disagreement survived the scrutiny. What began as a small tension turned into a stubborn fracture in our picture of the cosmos. Why should you care about a quarrel in the second decimal place of an obscure constant? Because this rate, this expansion speed, is not just a detail at the edge of a textbook. It threads through almost everything in modern cosmology. It sets the age we assign to the universe. It helps determine how far away distant galaxies truly are. It shapes the timeline for when the first stars ignited, when galaxies merged, when clusters assembled. Change it, even a little, and the cosmic calendar shifts from top to bottom. Simply put, we have built our grand story of the universe on one key number, and two of our best methods now insist that it cannot have the same value everywhere at once. Our standard model of the cosmos is a minimalist masterpiece. It assumes that, on large scales, the universe looks the same in every direction and at every location. It folds in ordinary matter, dark matter, and a smooth component that behaves like a constant pressure in the fabric of space, with only a handful of parameters. It explains the shapes of the ripples in the ancient light, the large-scale distribution of galaxies, and the overall pattern of cosmic evolution. For years, that model has fit data with uncanny precision. The tension in the expansion rate feels like a seam in a well-tailored suit that will not stay shut. You can reinforce the stitching. Add a small dart here, a subtle hem there, but as more measurements arrive, the same spot keeps straining. Some researchers try to strengthen the thread by examining every possible source of error. Others consider changing the fabric itself, modifying the properties of dark energy or adding light, fast-moving particles to the early universe. Each change has to be delicate, enough to adjust the expansion rate in one era without ruining the agreement elsewhere. Beneath all these efforts lurks a deeper question. Is the problem really with our instruments and assumptions, or is it with the portrait of the universe we have come to trust? How confident can we be that space behaves the same way in every direction and at every cosmic time, when a basic quantity like the expansion rate seems to depend on which cosmic era you interrogate? There is a more radical possibility, one that feels strangely old and startlingly new at the same time. What if space itself carries a subtle, global motion we have not yet accounted for? Not a dramatic whirl that flips galaxies end over end, but a slow, almost ghostly rotation of the entire cosmic frame. If the stage on which everything moves is not perfectly still, then the way light travels, and the way we interpret its stretching, could be biased in a way that only shows up when we compare the deepest past to the immediate present. At first hearing, a rotating universe sounds like something from an early 20th century dream, a mechanical sky with everything pinned to a spinning wheel. But modern geometry allows for a more delicate form of rotation, one that belongs not to matter swirling in space, but to the fabric of space-time itself. In such a cosmos, no single galaxy would feel flung outward. Local physics could look almost identical to what we observe. Yet over billions of years and vast distances, the paths that light follows would be tilted ever so slightly. If that tilt exists, even in a very mild form, then the messages we read from the ancient Afterglow and from the nearby galaxies might be written on two subtly different canvases. The early light would have journeyed through a cosmos that had barely begun to twist. The nearer galaxies would send their signals through a geometry that has experienced more of that slow turn. Each method would then be honest, each clock faithful to its own frame, and the mismatch we see would be a quiet testimony to an overlooked feature of reality. We stand between these possibilities, and the space between them is unsettling. On one side lies the comforting idea that everything is fine, that hidden errors will eventually be uncovered, and that the standard model of cosmology will emerge untouched. On the other side lies the admission that our map of the universe is incomplete in a fundamental way, which is more daring to cling to a successful model in the face of persistent tension, or to entertain the notion that the entire cosmic stage might be more complex than we assumed. You do not need to read equations to feel what is at stake. When you set your watch by a satellite, you trust that its orbit and its timing have been understood. When the devices that set our cosmic clock disagree, we are forced to confront how much of our knowledge rests on layers of calibration and belief. How often have we mistaken the consistency of our methods for proof that our picture of the world must be final? Think of a navigator crossing a featureless ocean. The map in their hands has worked for years. Stars rise where they should. Islands appear where the chart predicts. But there is one harbor that never quite matches. No matter how many times the journey is repeated, the harbor is a little nearer or farther than expected. At what point does the navigator stop blaming the waves, the compass, and the weather, and start asking whether the grid printed on the map is slightly warped? We are that navigator, and the harbor is the true value of the cosmic expansion rate. The ancient light and the nearby galaxies are the lighthouses we sight along the way. They are steady, bright, and carefully measured, yet they refuse to line up on the same grid. Somewhere between them, something in our understanding bends. In the story that follows, we will climb the ladder of distances step by step, read the diary written in the first light of the universe, and follow a daring proposal that a faint global rotation could be the missing term that finally brings our two cosmic clocks into a single, unsettling agreement. If this cosmic tension draws you in, please like and subscribe to the Quiet Universe channel. A dark dome filled with stars looks calm, but to astronomers, it is a grid of measurements waiting to be stitched together. Every twinkle carries a hint of distance, yet there is no single ruler long enough to span the cosmos. So we build a ladder of light, rung by rung, each step depending on the one below. The closer rungs are built on geometry we can touch. The higher ones rest on faith in patterns that repeat across galaxies. The entire story of how we measure the universe depends on this fragile chain. The first rung begins close to home, inside our own solar system. Here, distances are not guesses but triangles. Laser beams bounce off the moon. Radar pulses measure the spacing between planets. The scale is precise. From these known baselines, we learn the distances to nearby stars by watching them shift slightly against the background as Earth moves around the Sun. That tiny wobble, called parallax, was once invisible to the naked eye. Now, satellites like Gaia measure it for millions of stars with micrometer accuracy. The first few rungs of the ladder are solid steel. But beyond that parallax limit, geometry fails. The stars blur together into a tapestry too deep for direct measurement. To climb higher, astronomers turn to beacons whose brightness can be predicted. Among the most reliable are a class of pulsating stars called Cepheids. They rhythmically grow brighter and dimmer, their period of variation tied to their true luminosity. By comparing how bright they look from Earth to how bright they should be, we can infer distance. It is as if the universe had installed standard bulbs in the dark, flashing at regular intervals so that anyone who watches can tell how far away they are. Once Cepheids had set the scale for nearby galaxies, another rung appeared. Some galaxies host Type Ia supernovae, stellar explosions that reach nearly the same peak brightness. Because they are visible across vast distances, they act as reference beacons that connect our local yardsticks to the farthest edges of observation. By comparing the apparent brightness of these supernovae to their host galaxies' distances derived from Cepheids, we calibrate the absolute scale of the universe. The ladder extends from our solar neighborhood to the edge of the observable cosmos. Every rung is checked, recalibrated, and occasionally replaced. Errors at the base ripple upward, magnifying uncertainty the higher you go. If a parallax measurement is off by 1%, the same percentage error can inflate to several percent by the time you reach the galaxy's billions of light years away. The cosmic ladder is elegant, but it is also fragile. A misplaced assumption about the brightness of a class of stars, or unnoticed dust that dims their light, can shift the entire expansion rate we derive from it. Simply put, measuring the universe is like building a scaffold into fog. You can see the first few steps clearly, but beyond that, you trust patterns and proportions. Each rung depends on the stability of those below, and the fog never truly clears. For much of the 20th century, the cosmic distance ladder was the dominant tool for gauging the universe. It was the framework that allowed astronomers to convert redshift, the stretching of light, into an actual expansion rate. It was through these steps that Edwin Hubble, using Cepheids, first discovered that distant galaxies are racing away, implying that space itself is stretching. That revelation transformed our understanding of the cosmos, but it also introduced a dependence on calibration that would haunt every later attempt to refine the expansion rate. Over time, new rungs were added. Megamasers, natural microwave lasers orbiting the centers of galaxies, provide purely geometric distances when their orbits are mapped. Mira variables, a fainter type of pulsating star, add independent checks. Each new method strengthens confidence while also complicating the picture. The more instruments you add, the more chances there are for disagreement. Still, each technique points toward the same surprising conclusion: today's universe appears to expand faster than the one predicted from its early light. Why does that matter? Because the latter's result is not just a number, it is a test of our cosmic blueprint. The entire LCDM model, the standard cosmological framework, predicts how fast space should grow given its matter, energy, and curvature. When the latter insists on a higher rate, it hints that the ingredients or the recipe might be incomplete. A small inconsistency becomes a question about the stability of everything we think we know. Picture a craftsman using two measuring tapes to build a bridge. One tape starts at the shore, calibrated from the local ground. The other is extended from a distant tower, tied to a separate reference. If the tapes disagree by even a few centimeters, the bridge's halves will fail to meet in the middle. That is what cosmology faces now: a beautiful, near-complete structure whose final planks refuse to align. The human element is inescapable. Every correction, every reanalysis, reflects our determination to fix what seems broken. Yet each fix introduces its own assumption. We may underestimate dust in one galaxy, or overcompensate for metallicity in another. We are searching for perfection in an instrument that measures through billions of years and trillions of kilometers. There is humility in realizing that, despite all the precision, we are still guessing the scale of everything from the dim flicker of ancient light. Astronomers are meticulous in testing their rungs. They cross-check Cepheid distances against geometric masers. They observe the same galaxies with multiple telescopes, chasing consistency. They even test for local anomalies, such as whether our region of space might be unusually underdense or overdense, skewing the apparent expansion rate. None of these checks have resolved the discrepancy, say. Instead, the tension has persisted, echoing through every new dataset. At its core, the distance ladder is both triumph and trap. It has given us a universe we can measure, yet it locks that universe to the assumptions of its design. Every improvement in calibration refines our understanding, but also reminds us how far from certainty we remain. Could it be that the ladder itself is not the problem, but the assumption that one ladder can reach every corner of the cosmos? You can almost imagine space itself whispering, "Measure me differently." The next chapter turns from our man-made scaffold to the universe's own memory, the faint afterglow that remembers everything. Before there were stars or galaxies, the universe was a fog of light and matter so dense that photons could not travel freely. Every particle of light collided almost immediately with an electron, trapped in an endless dance of scattering and absorption for nearly 400,000 years after the beginning. This opaque plasma pulsed like a living body, its density rising and falling in slow, resonant waves. When the universe finally cooled enough for electrons and protons to combine into atoms, the fog cleared in an instant. Light broke free and began its long journey across space. That release left an afterglow that still surrounds us, a cosmic memory frozen in all directions. That faint light is what we call the cosmic microwave background. It is everywhere, washing over Earth with the uniformity of a perfect sea. Yet if you look closely, it is not perfectly smooth. Fluctuations, only a few millionths of a degree warmer or cooler, paint subtle mottled patterns across the sky. Those patterns are not random noise. They are the fossil echoes of the very first structures in the cosmos, the seeds of every cluster and galaxy that would later form. Within those ancient ripples lies a record of the universe's size, age, and composition. When scientists first mapped this background with satellites, the result looked almost featureless. Then, as detectors improved, delicate peaks and troughs emerged. The wavelength and height of those peaks carry information about how matter and energy were balanced at that time. The shapes of the ripples tell us how fast sound moved through the primordial plasma. By measuring the scale of those patterns on the sky, cosmologists can infer how big the universe was when the light was released, and from that, how fast it must be expanding now. At first, This analysis seemed to confirm what the distance ladder suggested. Both methods painted a picture of a universe around 13 billion years old, filled mostly with dark matter and dark energy. But as precision grew, subtle differences sharpened. The afterglow seemed to whisper a slower expansion rate than the latter insisted upon. To the cosmic background, the universe's pulse was calm and steady. To the ladder of galaxies, it was racing ahead. Somewhere between these epochs, something was being lost in translation. The beauty of the afterglow is its simplicity. It is a snapshot from a time when physics was straightforward gravity, radiation, and a nearly uniform soup of particles. Unlike galaxies, it is untouched by the complexities of star formation or interstellar dust. This purity makes it our most reliable witness to the early universe. Its tiny irregularities are like fingerprints, unique and detailed, giving us a map of conditions that prevailed long before the first stars were born. At its core, this radiation functions as a cosmic Rosetta Stone. It lets us translate between the deep past and the present. The angles between the hot and cold spots correspond to actual physical distances in the early universe. By knowing the sound speed in that plasma, we can convert these angular scales into a measure of the cosmos's geometry. If space were curved like a sphere, those spots would appear larger. If it were curved like a saddle, they would appear smaller. They match almost perfectly with a flat universe, a result so elegant it became a cornerstone of modern cosmology. Simply put, the cosmic microwave background gives us a baby picture of the universe taken with perfect exposure, and we have learned to read its light as if it were a text written in temperature. Yet reading that text is not easy. It must be filtered through instruments sensitive enough to detect changes smaller than 1/10 of a millionth of a degree. Detectors mounted on satellites such as COBE, MAP, and Planck have scanned the sky for years, each one peeling back layers of noise. The data are processed, cleaned, and translated into a power spectrum that looks more like a music score than an image. Each peak corresponds to a harmonic of sound waves that once rippled through the cosmic fluid. Fitting a theoretical curve through those peaks gives cosmologists a model of how the universe evolved. When the Planck mission released its final data, the precision was breathtaking. The expansion rate derived from the afterglow settled at about 67 kilometers per second per megaparsec. The uncertainties were so small that this number looked definitive. But then came the realization it was still a few units below the value measured from the local universe. The discrepancy was too large to dismiss, yet too small to feel catastrophic. It hung in a peculiar limbo between error and discovery. Why is that difference so stubborn? Because the cosmic microwave background measures the expansion indirectly. It does not watch galaxies move apart. It calculates the present rate by running the laws of physics forward from the early universe. If anything in that law book is incomplete, if dark energy or dark matter behaves differently than assumed, then the projection can drift. The latter, by contrast, observes the expansion directly through light shifts of nearby galaxies. Both can be right inside their own domains and still disagree when compared across billions of years. To understand how that could happen, imagine you are listening to a symphony recorded in a vast hall. The first notes echo with clarity, and you can reconstruct the size of the room from the reverberation. Now imagine that the air in the hall slowly changes density over time. If you replay those notes today, the echoes would no longer match. The recording would still be true to its moment, but the conditions under which you interpret it would have shifted. The universe's afterglow is like that recording. It is faithful to its own age, but we might be replaying it in a slightly altered hall. In everyday language, the afterglow tells us what the early universe believed the expansion rate should become, while the distance ladder measures what it actually is now. Each new mission tightens the uncertainty, but none erase the mismatch. Scientists have tried adding parameters to the standard model, allowing the number of neutrino species to vary, changing the ratio of dark matter to dark energy, tweaking how fast the universe transitioned from radiation to matter domination. Each tweak improves one side and breaks another. The cosmic background remains a stern teacher, unyielding in its lesson. Its peaks and troughs stay fixed, a reminder that the early universe was ruled by a clock that ticks to a slightly different rhythm. Why does it matter that this clock runs slow? Because if the afterglow is correct, then something in our understanding of late-time acceleration must be missing. Perhaps dark energy is not constant, but evolves over time, changing the pace of expansion in ways too subtle to see locally. Or perhaps gravity itself behaves differently on scales larger than clusters of galaxies. Each hypothesis stretches the framework of cosmology in a new direction, testing how much the universe can bend before the picture breaks. For ordinary people looking up at the night sky, the idea that the cosmos remembers its childhood may seem poetic, yet it is also practical. Without the afterglow, we would not know the age of the universe, its shape, or even that dark matter exists. The faint hum of microwave light in every direction is the foundation of our cosmic map. If that foundation is even slightly off, then the entire structure of modern cosmology could need repair. There is something deeply human about using light from before the first stars to question our present. We are reading a message that has traveled for 13 billion years, and finding that it contradicts the newer messages arriving from our own neighborhood. It is as if the universe itself has written two versions of its autobiography, each accurate to its moment, each confident, and we are left to reconcile the story. The next chapter will gather new witnesses, independent of both latter and afterglow, to test which version of the cosmic biography can withstand the cross-examination of evidence. In science, disagreement is supposed to fade with precision when better instruments arrive. When more data pour in, the error bars shrink and the answers converge. But in cosmology's greatest paradox, the opposite has happened. Every new cross-check meant to heal the split between the early and late universe has instead deepened the divide. What began as a statistical wrinkle has become a stubborn scar across the face of modern physics. The latter and the afterglow are like two witnesses giving conflicting testimony about the same event. To resolve their contradiction, astronomers called more witnesses to the stand. These new voices come from different corners of the universe, each speaking in its own dialect of light and motion. Some are megamasers orbiting supermassive black holes, their radio waves forming a geometric ruler free of assumptions. Others are time delays in gravitational lenses, where the light from distant quasars bends around intervening galaxies and reaches us through multiple paths. Each arrival time offers a way to measure cosmic expansion independent of both the latter and the afterglow. The hope was simple, an unbiased tiebreaker. The megamasers spoke first. They orbit so close to their host black holes that astronomers can track their Doppler shifts and proper motions over time, directly mapping their orbits in 3 dimensions. From geometry alone, the distance to their galaxies can be computed. No intermediate steps, no reliance on standard candles. When these distances were combined with the redshift of the host galaxies, they produced a value for the expansion rate that landed close to the latter's faster number. The local universe seemed to insist once again that space today is stretching quicker than the early light predicts. Then came the lenses. Imagine a bright quasar far behind a massive galaxy. The galaxy's gravity acts as a lens, bending the quasar's light into multiple images that flicker with time, delays of days or weeks. By measuring these delays and modeling the lens's mass distribution, astronomers can compute absolute distances. The result should be immune to local calibration errors because it depends only on general relativity and observed geometry. Yet the lensing results also pointed toward the higher, faster expansion rate. Another independent voice joined the local side of the argument. So the pattern grew the closer the measurement was to our own cosmic neighborhood. The faster the universe seemed to be expanding. The farther back you looked, the slower the inferred rate became. The split was not a simple gradient that could be smoothed away. It was a discontinuity that refused to vanish. The cross-checks multiplied but did not reconcile. Instead of converging, they formed 2 distinct camps, the early cosmos and the late cosmos, each internally consistent but mutually incompatible. In plain terms, The universe is like a choir where every section sings perfectly in tune within itself, yet the harmony between them never quite matches. Some researchers began to suspect that we might live in a slightly special region of the universe, a cosmic bubble where density or motion differs from the average. If our local space were a little emptier than its surroundings, galaxies nearby would appear to recede faster, mimicking an accelerated expansion. This idea, called the local void hypothesis, offered a tempting fix. It could explain the higher local measurements without altering the early universe. But careful surveys of galaxy distributions have shown no evidence for such an enormous underdensity. The void, if it exists, would have to be far deeper than anything observed, and that would create other contradictions. Another cross-check came from the ripples of sound still visible in the clustering of galaxies, known as baryon acoustic oscillations. These fossil waves are the descendants of the same oscillations imprinted in the cosmic microwave background. Measuring their scale at different distances provides a ruler for cosmic history. The results matched beautifully with the early universe's slower expansion rate. The rift remained. The galaxy's large-scale patterns sided with the afterglow, while local rulers and lensed quasars favored the latter. Why does it matter that so many voices refuse to harmonize? Because the tension is not just a mismatch of numbers, it is a test of whether our fundamental picture of reality is self-consistent. Every experiment that agrees with one side and not the other forces theorists to decide whether they trust the laws that govern the young universe or the observations that describe it now. If the laws are perfect, something in the data must be skewed. If the data are flawless, the laws may need rewriting. The temptation is to split the difference. Perhaps the expansion rate evolves slightly faster than the simple model predicts, or perhaps dark energy behaves differently in different eras. But the beauty of cosmology is that the equations are tightly bound. Tweak one corner and you risk unraveling the rest. Change how fast the universe expands, and you also change how structure forms, how stars cluster, how gravitational lensing patterns unfold. Every fix must be tested against a web of interconnected observations, and most fail under that scrutiny. At its heart, this conflict is not about who is right, but about what we might be missing. Could there be a hidden ingredient? A subtle form of energy that escaped detection because it leaves no trace except through its influence on cosmic expansion. Some teams propose early dark energy, a temporary field that dominated the universe just before recombination and then faded away. If such a field existed, it could alter the sound horizon imprinted in the afterglow, bringing its inferred rate closer to the local measurements. It is an elegant idea, but it introduces a ghostly component with no independent evidence. To put it another way, each attempt to resolve the tension adds complexity to a model that once prided itself on simplicity. We are watching a clean equation gather new variables, each one a symptom of our uncertainty. The human side of this story is striking. In conferences, cosmologists now divide their presentations between early and late measurements, displaying two parallel columns of results. The gap, once described with caution, is now spoken of with a mix of frustration and excitement. It has become a measure of how little we truly grasp about the invisible forces shaping cosmic history. The tension is no longer an anomaly to be erased, it is a frontier. Why? It matters moments echo through every debate. If the discrepancy persists, it may signal physics beyond the standard model, something deeper than dark energy or modified gravity. It could reveal a link between cosmic expansion and quantum fields, or hint at new particles that alter the early universe's dynamics. The stakes are nothing less than the architecture of the cosmos itself. For a moment, imagine this conflict as a courtroom drama where every witness tells the truth. Yet the stories cannot align because the stage itself has changed between testimonies. Perhaps the early universe's geometry subtly differs from today's, not through curvature but through an overlooked twist in space-time. If so, the rift between early and late may not be an error at all, but a clue. Simply put, disagreement has become discovery in disguise. The more the data refuse to converge, the more clearly they trace the outline of something new hiding beneath our assumptions. The next chapter will explore what happens when we try to patch this fractured map, questioning whether to alter our rulers or the very rules that define them. When a map begins to split along its seams, the first instinct is to patch it. Add a correction here, a hidden parameter there, and perhaps the pieces will fit again. Cosmology has entered that phase. For years, the tension between the early and late measurements of the universe's expansion rate has refused to vanish, so scientists have begun to experiment with new ingredients. Some patches are small, meant only to smooth the wrinkles. Others are bold enough to rewrite the legend at the bottom of the chart. The question is no longer whether we misread the map, but whether the map itself is incomplete. The simplest fix is to revisit what we mean by dark energy. In the standard model, it is treated as a constant property of space, an invisible pressure that accelerates expansion. Its strength never changes. Its behavior is uniform in all directions. That assumption works remarkably well for explaining the universe from the time galaxies formed until now. But if dark energy varied slightly over time, even just for a brief era after the cosmic microwave background formed, it could reconcile the early and late measurements. The early universe would have expanded faster for a short while, shrinking the sound horizon and letting the afterglow predict a slower rate without contradicting local data. This idea is called early dark energy. It imagines a hidden field that briefly dominated the universe and then faded away, leaving no trace except a shift in how we read the sky. Simulations show that such a field could exist within the known laws of physics, but it would have to turn on and off with unnatural precision, too much of it, and the universe would expand so quickly that structures could not form, too little, and the tension remains. It is a delicate balance, like adjusting the temperature of a kiln to fuse glass without shattering it. At its core, early dark energy is an elegant patch. It repairs the statistical split while preserving the beauty of the broader framework. Yet it also feels like tuning a melody by ear instead of re-examining the instrument. The harmony returns, but we are left wondering if the pitch was correct to begin with. Simply put, it replaces one mystery with another. We no longer ask why two measurements disagree. We ask why a hidden energy field chose to fade at precisely the right time. Other patches reach further. Some physicists question whether dark matter is as passive as we think. In our standard picture, it interacts only through gravity, silently shaping the cosmic web. But what if a small fraction of it decayed over time, or converted into lighter particles? That slow transformation could change how the expansion evolves. It would tilt the latter and the afterglow toward each other without inventing a new force. The trade-off is that decaying dark matter alters the growth of structure, so the predicted number of galaxy clusters and gravitational lenses must still match observation. So far, the evidence has not yielded a clear verdict. A different approach challenges gravity itself. Einstein's general relativity has passed every local test, from planetary orbits to gravitational waves, yet it remains untested on truly cosmic scales. Modified gravity theories attempt to alter how curvature responds to energy at great distances. In these models, space does not expand under a single universal law. It may evolve differently depending on the density of matter around it. Some of these formulations can bridge the gap between early and late measurements. Others collapse under their own complexity, predicting effects that have never been seen. Each adjustment demands a price, and often that price is consistency. To put it another way, patching cosmology is like repairing an ancient tapestry. You can sew new threads where the fabric frays, but if you weave too many, the original pattern disappears. Why do these theoretical patches matter to people outside the field? Because they remind us that even our most trusted frameworks are provisional. The universe is not obligated to be simple just because our equations prefer it that way. Each model we build is a story about reality, and every contradiction is a chance to check whether the story still fits what nature tells us. There are more subtle adjustments too, tweaks that hide in the small print of cosmic history. One proposal suggests adding a new type of neutrino, a sterile cousin that interacts only through gravity. Another lets the dark energy equation of state vary slowly over time instead of staying constant. These solutions bend the curve of expansion just enough to ease the tension, but not enough to transform the entire model. They are cosmetic surgeries, smoothing the surface without confronting the foundation. For now, none of them have provided a decisive cure. Meanwhile, observational teams continue to test every link in the chain: more precise parallax measurements, cleaner supernova samples, sharper cosmic microwave background maps, and new gravitational lens catalogs all add pressure. Each dataset makes the gap clearer. If the universe could speak, it might say, "Stop patching and start listening." The insistence of the evidence has forced cosmologists to contemplate what once seemed unthinkable. Maybe the geometry of space itself holds an unrecognized degree of freedom, something that can mimic acceleration without invoking an external field. That possibility leads into strange territory. Suppose space-time can twist as well as stretch. Not a spin that hurls galaxies through the void, but a gentle rotation of the underlying frame. In such a world, light from the early universe would travel through a geometry subtly different from the one shaping our local measurements. The mismatch would not be a failure of observation, but a reflection of that hidden motion. It would be as though we built our map on a turning table, unaware that the grid beneath our feet was slowly rotating while we traced it. For now, this remains a speculation, a whisper among more cautious ideas, but its appeal lies in its honesty. It does not pretend the fabric is flat. It accepts that the cosmos might have properties we have yet to name. It does not patch the old map. It asks whether the map itself needs a new projection. Why it matters lines echo through the debate. To change the rules of cosmology is to admit that we are still near the beginning of our understanding. The tension in the expansion rate becomes a symbol of how fragile our certainties are. What we call dark energy or dark matter may turn out to be artifacts of deeper geometry, concepts as temporary as epicycles in ancient astronomy. Each potential fix forces us to confront the limits of our imagination. We can view this era of patchwork not as failure, but as progress. Disagreement is how science breathes. A map that never changes is one that stops teaching us where we are. Perhaps the real discovery is not any single solution, but the realization that the universe is inviting us to rebuild our instruments of thought. The next chapter turns toward a daring interpretation of that invitation, the hypothesis that the cosmos itself might possess a near imperceptible rotation, a slow spin that bends the meaning of distance and time. Imagine standing on a wide plain that appears utterly still. The air is quiet, the horizon motionless, every direction identical. Yet after long observation, you notice a faint drift in the stars, a slow, collective turning that cannot be blamed on your eyes. The universe, for all its calm, might be rotating so gently that it takes 1,000,000,000,000 years for a single revolution. That idea sounds almost poetic, yet a few cosmologists have begun to test whether such a hidden motion could reconcile the two cosmic clocks that refuse to agree. The notion of a spinning universe is older than it seems. In the early 20th century, before the cosmic expansion was confirmed, some theorists wondered if the universe could rotate as a whole. Later, when Einstein's equations were explored in detail, they revealed that rotation is not forbidden by general relativity. A space-time can, in principle, have a global vorticity, a property describing how neighboring points twist relative to one another. In a small region, such effects are negligible. But across the entire cosmos, they could leave subtle fingerprints in the light that reaches us. Why would anyone revive this ancient idea now? Because every conventional patch to the Hubble tension has introduced new unknowns that feel increasingly artificial. Dark energy that switches on and off, dark matter that decays, gravity that morphs with scale. All are clever, but none are satisfying. Rotation offers a different angle. It does not add a new ingredient. It changes how we interpret the stage itself. If spacetime carries a small angular momentum, the apparent expansion rate could differ slightly depending on direction and epoch, creating exactly the pattern of disagreement we observe. At first glance, the suggestion seems at odds with the measured isotropy of the cosmic microwave background. The afterglow is uniform to 1 part in 100,000. Any large spin should smear that symmetry. But the math allows for a twist so mild that it would remain invisible at current resolution. A rotation period of roughly 500 billion years would be enough to nudge the local expansion without breaking the global balance. It would be the cosmic equivalent of a giant wheel turning once while galaxies live and die upon its rim. In plain terms, this rotation would not fling matter around like a spinning top. It would simply tilt the grid of spacetime itself. Light traveling through such a geometry would experience minute directional biases, altering how we read redshifts and distances over billions of years. These small shifts could accumulate, making nearby galaxies seem to expand away faster than those seen in the afterglow. The two clocks, early and late, would then tick at different apparent rates, not because of measurement errors, but because they belong to slightly rotated frames of reference. To put it another way, the cosmos may not only expand, but also twist, and we have mistaken the combination for a conflict in speed. The challenge is proving such a whisper exists. Rotation at that level would leave only the faintest signatures. One clue might hide in the polarization of the cosmic microwave background. If space itself has a gentle swirl, the polarization pattern of the ancient light should show a corresponding rotation, a small preference for one orientation over another. Another test comes from the distribution of galaxies on very large scales. A global twist would introduce correlations in their alignments, as if the entire cosmic web had been stretched slightly along a preferred axis. Astronomers have searched for these signals, and the results are, as yet, inconclusive. Some surveys hint at tiny anisotropies, patterns that could be explained by a slow rotation, but they could just as easily arise from statistical noise or local motion. The data are whispering, but too softly to be sure. What makes the idea linger is not evidence, but elegance. Unlike other explanations, a rotating universe arises naturally from the same equations that describe everything else. It demands no new particles, no exotic forces, only a small relaxation of an assumption we made long ago, that the cosmos has no preferred direction. Why would a universe spin at all? Angular momentum is nearly universal in nature. Atoms spin, planets spin, galaxies spin. Perhaps the cosmos inherited a faint trace of that motion from whatever process birthed it. If the early universe carried even a hint of rotation, cosmic inflation could have stretched that spin to a scale large enough to influence observations today. The result would be a universe so vast that its turning is imperceptible within human timescales, yet not entirely zero. Critics remind us that extraordinary ideas require extraordinary proof. A rotating cosmos must satisfy strict tests. It must not introduce observable shear in galaxy shapes, nor distort the cosmic microwave background beyond its tiny fluctuations. The rotation would have to be global but weak, coherent but subtle, detectable only through the harmony of thousands of independent datasets. Some argue that we are chasing ghosts, mistaking noise for novelty. Others see in this pursuit a necessary boldness, the kind that once allowed us to imagine an expanding universe in the first place. There is also a psychological allure to the concept. It restores motion to the universe in a profound way. Expansion feels abstract, a stretching of emptiness. But rotation is something we can imagine. It gives the cosmos a body, a rhythm. If true, it would mean that our position in space is not just moving outward with the flow of expansion, but also slowly curving through a larger rotation, like passengers on a carousel too vast to perceive its turning. Simply put, the idea transforms the universe from a static backdrop into a living system with internal dynamics we have yet to grasp. Why does it matter? Because it shows that even at the scale of the whole cosmos, geometry may carry hidden complexity. What we call the tension between early and late measurements could be the first experimental hint that space-time itself has structure beyond expansion. A rotating universe would still obey relativity. It would simply include an extra term in its equation, one that tells us how the whole fabric is twisting as it stretches. The most remarkable aspect of this hypothesis is that it can be tested. Future polarization maps of the microwave background, combined with gravitational wave observations, will have the sensitivity to detect or rule out such rotation. Gravitational waves themselves could carry directional imprints, a subtle chirality that would betray a global spin. These are not unreachable dreams, but measurements already planned for the coming decades. The cosmos may be silent to our ears, but it hums in wavelengths we are finally learning to hear. If the tests find nothing, the idea will fade gracefully. Another attempt filed in the long archive of cosmological imagination. But if even a trace of rotation is confirmed, it will change how we think about everything. The universe will no longer be the inert frame of all motion, but a participant in its own dance. The two conflicting clocks will finally tell the same time, not because we forced them to agree, but because we realized they were reading from slightly tilted pages of the same story. There is a quiet thrill in knowing that such a simple adjustment could reconcile decades of discord. It reminds us that the universe's mysteries often hide not in its parts, but in the assumptions that bind them. When we finally learn whether space itself turns, we will have answered a question older than science: does stillness truly exist? Or is motion the rule even at the scale of everything? The next chapter will follow the trials designed to test these bold ideas, to measure the cosmos as if it were a vast wind tunnel where every current and rotation leaves a trace. Every theory that dares to reshape the cosmos must one day face the courtroom of evidence. For the rotation hypothesis and its competing ideas, that day is approaching. The coming years promise a flood of data from instruments built with one mission to decide which of our cosmic clocks is telling the truth. The stakes are high. A new experiment might vindicate a subtle spin in space-time, or reveal that the universe is, after all, perfectly still. Either outcome will redraw the boundaries of what we consider certain. Science advances by prediction. A theory that cannot make a testable forecast is philosophy dressed in numbers. For cosmology, predictions are tricky because they must reach across time and scale, translating abstract geometry into patterns of light we can measure. Each new hypothesis born from the Hubble tension must therefore leave a trace we can search for, a signature in the microwave background, a drift in galaxy alignments, or a deviation in gravitational lensing. Testing these requires patience and precision, and an acceptance that we may spend decades proving ourselves wrong. Among the first trials will be deeper maps of the cosmic microwave background polarization. If the universe carries even the faintest rotation, the orientation of this ancient light should twist slightly as it crosses the sky. Upcoming missions like the Simons Observatory and Lightbird will scan the heavens with sensitivity an order of magnitude better than before. They will look for a specific pattern known as B-mode polarization, a swirling arrangement that could betray either primordial gravitational waves or global vorticity. The difference is subtle but measurable. A positive detection would electrify cosmology. A null result would push the idea toward the shelves of beautiful but empty possibilities. Another set of predictions arises from gravitational lensing. A rotating universe would not only affect light from the early cosmos, but also change how intervening matter deflects light on its way to us. The deflection patterns would show minute anisotropies, small preferences in direction that align with the hypothetical spin axis. Upcoming surveys, such as Euclid and the Vera Rubin Observatory's legacy survey of space and time, will trace billions of galaxies, measuring these distortions with exquisite accuracy. Their data will either expose the telltale alignment or close the door on global rotation for good. Simply put, the universe is about to undergo its most thorough cross-examination in history. Yet rotation is not the only theory on trial. Early dark energy models predict specific shifts in the timing of structure formation. Decaying dark matter leaves fingerprints in the abundance of clusters. Modified gravity alters how galaxies drift within cosmic filaments. Each of these frameworks writes a different melody into the same cosmic score. The task before us is to listen closely enough to hear which notes ring true. None of these predictions are free. They demand immense investments of time, resources, and human focus. For every bold new hypothesis, thousands of hours of telescope time and millions of lines of code will be devoted to testing it. Why does it matter that we test them all? Because cosmology sits at a unique crossroads between mathematics and meaning. When we change a parameter in our model, we change the implied age of the universe, the formation of galaxies, even the timeline of life's possibility. Each revision cascades through everything else we think we know. A faster expansion rate shortens the cosmic age by hundreds of millions of years. A slower one lengthens it. To be wrong here is not a minor accounting error. It is to misunderstand the tempo of existence itself. At its core, prediction is a moral act. To make a claim about the universe is to invite correction by reality. In that correction lies progress. If the next generation of data shows no sign of spin, then we will have learned something profound, that even the boldest geometric interpretations cannot escape the discipline of observation. If, however, the data reveal a consistent tilt, then we will be forced to rewrite textbooks, redefining not just how space expands, but how it moves. Why it matters lines echo through every observatory preparing to join the search. Precision cosmology is more than a race for numbers. It is a rehearsal for humility. Each telescope, each sensor, each beam of microwaves collected from the sky represents an act of listening. The cosmos does not explain itself. We interpret its silence and call it knowledge. To discover that our interpretation is incomplete is not defeat, but permission to begin again. There is also a personal price to being wrong. Whole careers have been built on the assumption that the standard model of cosmology is correct in its essentials. A confirmed rotation, or any other departure from that model, would unsettle decades of carefully tuned results. Distances would have to be recalibrated, simulations rewritten, parameters refitted. For younger scientists, it would be thrilling. A chance to work at the frontier of a new paradigm. For veterans, it might feel like watching a familiar map dissolve, but that is the rhythm of discovery. Every generation inherits the tools of the last and then learns where they bend. To put it another way, progress in cosmology is not a straight line, but a spiral. Each revolution brings us closer to the truth, even if it feels like we are circling the same questions. The next decade will also bring independent tests from gravitational wave astronomy. Binary neutron star mergers act as standard sirens, emitting both light and gravitational waves. By comparing their distances inferred from light with the distances derived from the waves, scientists can measure the expansion rate without relying on any ladder or afterglow. A consistent mismatch between standard sirens and other methods could reveal which cosmic clock is faithful. These events are rare but growing in number. The universe, through its most violent collisions, offers us a new way to check our arithmetic. There is poetry in this process. We began by watching stars flicker, then listening to the faint radio hum of ancient light, and now we wait for ripples in space-time itself to settle the argument. The tools grow more refined, but the questions remain primal. How fast are we moving? How old is the sky? What kind of law keeps time for the cosmos? Each answer is provisional, each correction an act of courage. The price of being wrong is paid in pride, but the reward of being corrected is knowledge that lasts longer than any single model. If the coming tests reveal no hidden spin, cosmologists will return to the data with new humility, perhaps discovering subtler errors in the ladders or assumptions about the early universe. If they do find rotation, they will face a new challenge explaining why such a property exists and how it began. In either case, the result will reshape the boundary between known and unknown. The philosopher's question lingers: is truth a destination or a process? In cosmology, it is clearly the latter. Each failure refines the lens through which we see. The universe does not change because of our theories, but our place within it does. Even wrong ideas, tested honestly, become stepping stones to deeper understanding. The next act will step back from measurement to meaning, asking what it tells us about our role in a universe that might be turning, and what kind of wisdom emerges when certainty gives way to wonder. Some questions are too large to close neatly. They circle back like comets, their orbits carrying them across centuries of thought. The universe's expansion is one of them. We began with a simple desire to measure how fast space grows, but we ended up confronting the limits of what we can know about reality itself. When the cosmos refuses to fit our equations, the failure is not only scientific, it is existential. What does it mean to live in a universe whose laws can shift under scrutiny, whose very stillness might conceal a slow, cosmic turn? It is easy to forget that all our measurements, all our data, come through the narrow window of human perception. We are clever, but small. We place mirrors in space, listen for faint whispers of ancient light, and call it understanding. The expansion rate, the rotation, the tension between clocks. All of it depends on how light reaches our instruments and how we interpret it. If the stage itself moves, or bends, or carries a hidden rhythm, our instruments will record that dance without ever seeing the dancer. Perhaps the paradox of the universe's expansion is not in the cosmos, but in our insistence that it stands still long enough for us to define it. Simply put, science gives us precision, but not peace. The more accurately we measure, the more sharply we feel the distance between knowledge and certainty. Every new observation is an act of faith that the universe will reveal itself in a consistent way. Yet consistency may be a local luxury. Maybe the universe is not a book written once, but a living script that rewrites itself as it unfolds. Throughout this investigation, we have treated the cosmos like a clock, its hands turning at rates we can compare. But perhaps that metaphor is too tidy. A clock presumes a maker, a purpose, and a single time for all who read it. The universe, by contrast, might be more like an ocean. Waves rise and fall, currents shift, and any sense of global rhythm is an illusion seen from the shore. When we say the universe expands, we are describing the motion of that ocean's surface. When we find tension between our measurements, we are discovering that different depths move at different speeds. The mystery of the two clocks reveals something human as well. We built our ladder of distances with care, one rung at a time, trusting geometry, light, and the regular throbbing of stars. We built our model of the early universe on equally solid ground, tracing the faint afterglow of its birth. Yet these tools disagree, as if reminding us that no system of truth can fully capture the whole. To know the universe is to accept contradiction as a companion, not a flaw. Why does it matter that we might be wrong? Because being wrong is the engine of progress. Every tension between theory and observation is a doorway to deeper understanding. The history of science is a sequence of paradoxes resolved by imagination. Light was once thought a wave, then a particle, now something that transcends both. Space was once a void, then a fabric, now perhaps a moving fabric with structure of its own. Each revision feels like loss at first, but it brings us closer to the unity that the cosmos seems to promise and yet withhold. At its core, the Hubble tension is a mirror. It reflects our relationship with the unknown. We crave a universe that is neat, harmonious, governed by simple constants. But the real universe might be untidy, improvisational, full of variations that we cannot yet resolve. Maybe perfection lies not in smoothness, but in the delicate friction between what is known and what resists knowing. The philosopher might say that we are measuring not only space, but humility. Every time our rulers fail to meet, the gap between them becomes a measure of our growth. To accept that the universe may rotate, or that it may behave differently than we imagined, is to step beyond the comfort of final answers. It is to recognize that knowledge is a process, not a possession. There is also something deeply poetic in the idea that the universe might carry motion, even in its quietest state. A global rotation, if it exists, would mean that every atom, every planet, every thought has been part of a single, slow dance since the beginning. We would be moving not just outward in expansion, but also around a hidden axis, like small notes in a cosmic symphony too vast to hear. Even if that rotation is never proven, the metaphor holds we are all turning together within a mystery that transcends measure. In everyday language, this search for the universe's true pace is a reflection of our search for meaning. We want to know whether reality has direction, whether time itself is linear or circular, whether the cosmos is a closed story or an endless rehearsal. The data may one day settle the numbers, but it will never settle the longing that drives us to ask. Why it matters lines ripple outward. If the universe is still, then our minds are the only things that turn, crafting motion from silence. If the universe truly spins, then everything we know participates in a motion older than light itself. Either way, we are not outside the story looking in. We are characters inside the unfolding of a reality that continues to write itself with every observation we make. To put it another way, when we measure the universe, we are really measuring the boundaries of human imagination. Our equations reach far, but there is always a remainder, an unmeasured fraction that hums in the background like static. That hum is what keeps science alive. Without it, curiosity would end. Every great discovery begins with dissonance, and every reconciliation begins with a question that will not fade. What if our map is incomplete, not because we drew it wrong, but because the territory itself keeps expanding in meaning as well as in space? What if the universe's refusal to fit is an invitation, a quiet beckoning toward deeper comprehension? At the end of this journey, the image remains two clocks, two truths, one cosmos. Whether the universe turns or stands still, whether its laws are timeless or evolving, it continues to exist beyond the reach of our certainty, and that is its greatest gift. The night sky will keep glowing, the ancient light will keep falling on our instruments, and we will keep asking how it all holds together. Perhaps the universe's greatest mystery is not how fast it expands, but why it lets us ask at all. What does it mean that a small species, on a pale planet, can look into the dark and sense both its silence and its motion, and wonder which one is real?